As I continue my work on the report, I'm now turning my attention to inference, so let's check the conditions for valid inference. I don't know that I have a random sample. I don't know anything about the sampling, and not knowing about the sampling is a bit concerning for me. I'm not sure who I can infer this to, even if I'm dealing with inferences in the past, in the early 50s. I'm not sure who we're talking about here. I'm not sure if these data were collected across this 2-year period in all sorts of locations in the United States, only in certain locations. So knowing something about the sample is going to be important to making inferences, and I don't know much about the sample at all here. I also don't know if the observations are all independent. There's not that many of them, so I'm hoping they are. Let me go ahead and check for normality and linearity and homoscedasticity. So let's see what we get from this. Oh, something's wrong with my plot here. Let's make sure I've run everything before. Let's try it again. All right, so what did I call the model? I called it the income temp model, and that's what I'm calling it here, income temp model. Residuals. So I've got an error message here. Let's see if I can figure out what's going on. Tells me that X and Y lengths differ. So let me actually try getting these values. I'm going to look at them separately. It's a dot. Fit at dot values, not underscore. Okay. Rather than turn off the recording, I thought you should be with me as I walk through trying to find errors, because that's going to happen to you sometimes. So let's go ahead and look now. All right, so here's our normal QQ plot. I actually like to have these in separate, in the same notebook. So let me go ahead and move this to another code chunk. Okay, so here's my QQ plot. Looks like I have some heavy tails here and here. Not terribly bad, but remember what heavy tails are going to do. Heavy tails are going to put more area out in the tails than you expect. That means when you set your critical value for your probability statements, you're actually going to have more area out than what you say. So if you're saying it's a 95% interval, it's actually going to be greater. It's actually going to be less than 95% confidence, because you're going to have a higher error rate. So if you're putting, to say it another way, probably I should have said this the first time, if you're putting 5%, for instance, in the tails, and you think you have 5%, so you're making statements about 95% intervals, when in fact you have 8% in the tails, then really you're calling a 92% interval, you're calling it a 95% interval. So that's a little bit of a concern. How many values do we have? 30 observations, 2 explanatory variables. I'm not going to be confident relying on the central limit theorem here. So I'm going to have some approximations with my probability. Checking now for linearity. I don't see, let me go ahead and put that line in there as well. Just helps us see everything. I don't see any systematic pattern in which we go up above and down below and up above, or vice versa, down below, up. So these are kind of scattered at random about that line. That's pretty good. So I'm thinking linearity is not an issue. I'm a little bit concerned, not overly, but again, we don't have many points to be able to detect whether we have heteroscedasticity, but it sort of looks as though I'm starting off here with very little variance here. I'm growing it a little bit further here, and then I'm growing it more in here. So remember my little trick I like to use. Go ahead and slice some lines. Let's say we slice a line at 0.30, 0.35, 0.40, and 0.45, and then look at the variability within those. From 0.25 to 0.30, very little. 3.0 to 3.5, well, we've got this one point here which makes it more, that one outlier, but otherwise about a little bit more than we had in the first category. When we go to the next category, about the same as the second category, and when we go to the fourth, even a little bit more yet. So not enough to convince me that this is going to be much of a problem, but I wish I had more points to look at. I really would like to do research here, another study where I understand sampling, where I have more points so that if there is heteroscedasticity, I can be more confident about declaring it. So all in all, I'm going to proceed, but I'm going to be really cautious about making statements about probability. And also remember, if we have heteroscedasticity, then the effects that we're observing are not actually, we don't have the same standard error for all along the values, the predicted values here. We don't have the same standard errors. And as such, when we look at our p-value, it may be different for one region than it is for another region. But we only have one overall p-values because we're only calculating a single standard error. If you look back up here, you'll see that we're only calculating a single standard error on our graph for each of these coefficients. Okay, so there's standard error, and then we have a residual standard error, a single standard error here that's used to calculate this p-value down here. So, all right, let's put this all together. Let's see what I'm going to say. I've got some things written here. I'm going to go ahead and bring them in. Do I have another figure yet, or is this? Oh, yes, I do have another figure. So this is figure 2. Okay. All right. What about if I say something like this? Let me go ahead and show the output only here. I am unaware of how these data were collected, so the purchasers may not be representative of all purchases in the early 1950s. I'm not certain of the characteristics of the population for which I'm trying to make an inference. Further, the normal QQ plot of figure 2 suggests that these data are not normally distributed, which further reduces my level of confidence in the above intervals, actually in the intervals below. We don't have the intervals yet. My 95% confident is now changed, or will suggest the intervals be taken as rough approximations regarding the slope coefficients. Okay, let's put in a few spaces and figure 2. Okay, and then down here, we're talking about linearity, and we're talking about heteroscedasticity. I'm going to say that this figure suggests some heteroscedastic trend with the variance of residuals increasing with an increase in predicted levels of consumption, the condition of linear relationships of income and temperature to consumption seems reasonable. Okay, and put in some space here and put in for figure 3. And let's go ahead and hide this code chunk. Okay. Okay. My inferences, I'm cautious about my inferences. As they are rough approximations in terms of probability statements. Let's see how it all looks. All right, so I note that I said in some, but that actually should come below actually creating those confidence intervals that I'm making those rough approximations for. So I need to do that. So let me add that. Okay, so there are my confidence intervals. What I'm going to do, though, is I'm going to hide this so that when we run it, we'll just see it up here in the console window, and we can get what we need from this. Let's see, I'm not sure I want to do it like that. I think I've actually written ahead of time a little statement. Oh, I did put the confidence intervals like that. Okay. Okay, I got that from right here. So that's my regression coefficient for income. Notice that it's a population coefficient. Okay, let me go ahead and put in some conclusions. If you're wondering where I got that p less than 0.01 for the model, if we go back up here to the model, I'm looking for here it is, nope, that's price. I'm looking for income temperature. Here it is, income temperature. Here is our multiple R squared that we knew about, 0.70. Here is our F statistic, 2 and 27 degrees of freedom, 2 degrees of freedom because of 2 predictors, 27 degrees of freedom because we take the number of values, 30 minus 1 is 29, and subtract the 2 predictors, and our p-value is very, very small, 0.0000007. I think I missed a O, but you get the point, 7957. Okay. So I should probably, let's see, I already said 70% of the variation, the amount of ice cream consumed. Model will work for a larger population represented by this sample. I have some confidence that after accounting for temperature, now I go ahead and those are my main findings having to do with how effective this is. So notice I don't put in all the specifics, and I don't put in the partials and semi-partials, and I don't talk about why I eliminated price from the model, because that would be repeating what I did up here. Instead, I'm trying to provide an answer to the research question. Okay. Okay, and then I need a press release. Ice cream has long been a popular dessert. A recent study of data about ice cream consumption in the early 1950s found that the amount of ice cream consumed was strongly related to temperature. The amount of ice cream consumed can be better explained by a model that includes both temperature and family income data. Study found that after taking the temperature into account, an increase in family income of $10 per week resulted in an average increase in consumption of between 0.01 pints and 0.06 pints per person. Similarly, after taking family income into account, an increase in temperature at 10 degrees Fahrenheit was related to an average increase in consumption of between 0.03 and 0.04 pints per person. Let me go ahead and take a final gander at this. Okay, I think it looks good. I'm ready to post it, send it in, and ready to end this video series on covariates. I look forward to seeing you in the next video series.